Alright, so basically we're going to talk about a little bit what this whole design purpose is. So for the design, what we want to try to do is that we want to try to recreate what the EMG is, because this has many different applications, and one of them are driven prosthetics. It's a super useful device that we can create based on what we've learned in class. So a little bit of background about this. What is the EMG? Well, that EMG stands for electromyogram, and what it basically does, or what it basically is a device that measures the difference in potential between 2 points relative to some distant ground. Many people use it, for example, if you have an amputated arm, or let's say a leg, etc. When you flex or contract your muscle, that is going to create a certain difference in potential between that part of your muscle, and then that's going to create a signal to this device that is going to tell it to do something about it, whether it's to flex, to rotate, whatever it is. But it basically acts as a switch. So a little bit about what this muscle contraction is about. So it's the electrical activity, as we said, that is associated with the muscle contraction, and it has an amplitude of 0.1 millivolts to 1 millivolts, more or less, pretty much, for a normal person who's not like, really bulk. And it has a frequency that goes around 10 hertz to 1000 hertz. So since our purpose is to build the hardware that is going to measure this muscle contraction activity, so we're going to be basically building an electromyogram, we have to take some things into consideration. First, we need to remember that there's some noise that is going to come with the signal. For example, we have postural and muscle activity noise, and those are frequencies that are usually equal or less than 10 hertz, which is very convenient because we're not cutting part of our muscle contraction signal. This postural muscle activity comes when we barely notice it, but if you close your eyes, you feel your body swagging, like moving back and forth. That is what this noise is referring to, and what we want to cut from our signal. We also have the noise that comes from the electrode tissue interface. This electrode tissue interface is going to create some sort of battery that is going to actually have, based on thermal fluctuations, its voltage is going to change, and it's going to have a frequency of less or equal to 1 hertz. And this is really important to get rid of because this can have thousands of millivolts that are going to affect our actual signal. Then last but not least, we have to worry about the Johnson noise. This usually has a frequency of 1000 hertz or greater, and this comes from the statistical fluctuations that happen when electrons go through a conductor. So now that we know what the noise part of the signal that we want to get rid of, we know what we want to do. We definitely want to have a filter that is going to get rid of signals that are greater or equal to 1000, more or less, and we want to get rid of any signal that is less or equal to 10 hertz. So we're definitely going to be using a filter over here, and as we can see, we need some amplification because, well, obviously, in this case, 1 millivolt is not going to be enough to tell the whole device, the prosthetic, to act as a switch and be like, well, we need to flex, we need to rotate. We're going to need to amplify the signal to at least 5 volts so that we can have a working hardware that is going to measure correctly this muscle contraction. So now I'm going to talk a little bit about the theory behind the elements that I'm going to use in my circuit. The first one is going to be the active filter. Alright, so as part of the introduction, as we were saying, it's important to know, just as a theoretical background, how active filters work. And this is an example of an active filter. Basically, you have an operational amplifier, and then you're going to have certain impedances down here, here, and here. This one we're going to call it C of I, this one's Z of F, this one down here C of 3. this basically works exactly as we've been working with operational amplifiers, just a tad differently when we're going to use them as filters. So in our case, we're going to be using the active bandpass filter. So how this is going to work is that basically we're going to have over here the part that is going to be the responsible for the high pass filtering, and then this is going to be responsible for the low pass filtering. The way that we can get to our h of omega is really easy. First, we're going to define what C of I is. C of I is basically the addition in series of these two elements, because we know they're in series. And then C of F is the parallel equivalent of the addition of these two. So if we just follow rules from circuits, we see that C of I is basically just going to be C of R of I, which is just Ri, and then the impedance of the Ci capacitor, which is 1 over j omega Ci. And then this, if we rearrange this a little bit with algebra, we get this for a result of C of I. Then for C of F, we're just going to do the parallel equivalent of these two. So we have 1 over Rf plus j omega C of F, because we know that the impedance for capacitors is 1 over this, and since we want 1 on top of that, then we just have this, and all of this to the negative 1. So we just inverse this, and doing some algebra, we get to the result that we're going to have C of F equal to Rf over 1 plus j omega Rf Cf. Now, that was the hard part. Now, the easy part is basically defining our transfer function as V out over Vn, and we know that for the inverting amplifier over here, operational amplifier, that is going to be negative Cf over Ci. So all we have to do is put these two together. So here we have negative Cf, which is this, times the inverse of Ci, which is this flipped, and we're going to multiply it times the cool type of 1, which is Ri over Ri, so that we see how we get our transfer function equal to negative Rf over Ri times the transfer function for the, in this case, this is the low pass filter, times the transfer function for the high pass filter. And this is going to be really useful when we're trying to analyze our results in data, because we're going to use this transfer function to get our h of omega, our g of omega, and that is going to be super easy, because all we have to do is do h of omega the same way we've been doing all along for the bandpass filter, and then we're just going to have to add 20 times log base 10 of our amplification. Alright, so for part of the introduction and the theoretical things that we should take into consideration, I'm going to explain a little bit how the ionate 126, the equation of the gain, is derived. So first of all, this is, I got this diagram from the spec sheet, and this basically gives us the values for the resistors, except for Rg in the diagram. And then it also gives us the final equation for the gain and what we get for V out. So our task is to, using a little bit of what we learned in circuits, to understand where this comes from. So first, what I decided to do is do some nodal analysis. So for the first equation, I analyzed node A, which I put over here. And we know that there's no current coming into the op-amp just because of our guidelines to working with operational amplifiers. And so the only currents that we're going to have is the one that is coming from node A up to V out, and then the one that is coming, and I decided the directions of the current, and the one from node A going down to the second operational amplifier through Rg, and then last but not least, we have the current that is going up to node A. So that is just illustrated over here, and from this equation we get this, which is V1. And why did I call it V1, node A? Because I know that whatever is coming into here, since this has negative feedback, we know that what is coming into here has to be the same coming out of here. So the V1, which is the V in plus, is going to be this right here, the voltage over here, which is the same voltage down at node A. So that's going to be V1 minus V out, so V1 minus the V out over the resistor K, 40K. So that's the current going through here. Has to be, if we add this current to the current going from V1 to V2, which is going to be just V1 minus V2 over RG, then this two have to end up, it's going to be this one, has to add up to these two. So this one over here is just going to be the, what I call here, down here, node B, so it's going to be VB minus V1 over 10K ohms. And I did the same pretty much for the other equations. For this one, this equation over here is representing node C, which is down here. And we remember again that the voltage right at node C is going to be equal to V2 because what's coming in here has to be equal to that. And we also remember that it's no current going into either of these. The same I did for number 3, but in the end we're going to see that number 3 I didn't end up using it. Down here is just, I just rearranged everything. So, for example, for the first one, I separated all the components that had V1, because we have one here, one here. So I put it all together, and the V2 separate, and then the VB, and then the V out. It's just basically rearranging this equation. The same for the second one, rearranging it, so we have separate components for the different voltage at certain points, and then the same for the last one. And to finalize it, what I did is that I took the second equation, which has a negative 1 over 10K, which was equal to this, and I took part of the first equation that also had a negative over 10K times VB. So I just substituted from the first equation into the second one to get this equal to, obviously, this side of the second equation. And then after that, all I did is I did the exact same thing, separate by voltage values. So this is just a rearrangement of this equal to that. And then down here I'm just adding up and putting it all together. And then we can see that we have V out equals V1 minus V2. And since we still had this factor, I just multiplied it over here to this side and this side. So we have 40 kiloohms over 8 kiloohms, and then plus 2 kiloohms over RG. So that's going to give us V out equals V1 minus V2 times 5 plus 8 kiloohms over RG, which is our gain. And that pretty much explains how the gain derivation of the ionate 126 works. And this is just going to be really important in our circuit because we're going to be using the ionate to measure an amplified part of our signal. Alright, so first of all, I want to talk about the design in general as the good and like entire big picture, because that is the way that I actually designed it. First, I thought what I wanted to measure and how I wanted to measure it, and then I went part by part, picking and selecting the different components and their correct values. So the big picture is this one. First, we have the de-amplifying of the signal. This part over here, I knew that we needed to have a small signal because our blue boxes aren't really good at having small amplitudes. So we needed something that will make the signal smaller. So in this case, I decided to use an inverting amplifier just because we've been using this a lot and we know how they work. And we know that the relation, and we're going to explain more in detail later, part by part, but we know that the relation is basically negative Ri over Rf, which it's very easy to think that, oh, maybe I can find components that can make the incoming signal be bigger than what I'm going to have as my output. So this part over here is the inverting amplifier, and as we said, this is going to be the de-amplifying signal, the part of the circuitry. This is not going to be connected to the arm when we do the actual trial. So from here to that side, that is no good for the trial, but we're going to use it for measuring data. over here, from here side to there, obviously we're going to be connecting it to the arm. So in this case we have V2 and V1 here. That is the V1 and V2 that we're going to connect to the arm. And obviously our ground electron is going to be connected to ground. In this case, what we did, or what I thought to do, is like, hey, well, this small signal that is going to come out from the de-amplifying part, I'm just going to connect it to the V2, and the V1 I'm going to connect it to ground. Because over here, we have an instrumentation amplifier. Basically what it is going to do is going to measure the difference in potential from here to here. So that was going to give me good data that was going to pretty much pretend to be the arm. So yes, as we said, this is the instrumentation amp. This, what it's going to do is to amplify and measure. And as we're going to see in the next part, this is going to be the part of the circuitry that actually determines the total amplification. Because when we move to this side, which is the active filter part, which comes from here, all of this part, this is the filtering and amplification. And again, we're going to be using an inverting amplifier, the LM747. What this part is going to do is that it's going to filter the signals that we want. Obviously, we're going to talk a little bit more in detail about this part when we talk about the cutoff frequencies that we decided to use. So it's also going to amplify, but the amplification is just going to be a byproduct of what we choose as our F2, CF2, our I2, and CI2. It's just going to be a byproduct, and the final gain that I want for my entire circuitry is going to be determined by this, because it's really hard to find values that serve both as filter and final amplification that we want. So it's really easy over here to come and switch this RG, just switch it to whatever gain we want, total gain, then try to mess up with the filtering part. So this is the filtering amplification. And then over here, this is basically just a simple LED circuitry. What it does is that I just thought, well, we need an LED to turn on whenever the signal coming from the arm is big enough. So since we're going to be filtering, hopefully, all of the bad frequencies that we don't really want, then we just needed a transistor over here that was going to measure when there was a certain, let's say, hopefully, 5 volts, and then the LED was going to turn on because we were connecting it also to a power supply over here, and then current will finally flow, etc. So this is just the LED circuitry. In this case, we use the 2N3904 transistor. So that's basically it. We have the LED circuitry, we have the filtering amplification, we have the amplification measuring, which all of this is for the arm. And then for measuring in data, we also have the de-amplifying of the signal. So this is basically the entire circuit. Now we're going to go part by part, explaining how we chose the components and the values for each one. Alright, so the first part of my circuit is the de-amplifying of the signal. And in this case, what it basically is going to do is that it's going to take the signal generated by the blue box and it's going to de-amplify, so make the amplitude of the signal smaller, so that we can, think of it as what a real arm would give us, which we know the range is about 0.1 millivolt to 1 millivolt. And these blue boxes don't really get to that small amplitudes, and if they do, it's kind of fluctuating. It's not really a good reliable signal. So that's why we're going to use the circuitry, so we can make measurements that are going to be useful for the arm. So basically this is an inverting amplifier, and in this case we're going to be using the LM747. And this is the circuit diagram that we've been thinking about or using even in class for what we call the inverting amplifier. We also know from class that V out over V in for this circuit is going to be negative RF over RI. So since all I wanted to do is to de-amplify the signal, I was like, okay, perfect. This is going to be our V out over V in, so I just need to pick one of these values and then make the other one match whatever I want. Whatever I want the de-amplification to be. So what I did is that I said, alright, well, I'm going to input in a signal of 100 millivolts, which is more reliable for the blue boxes. And then I want to get a signal that is about 10 millivolts. Why did I not pick 1 millivolt? Just because a bigger amplitude over here is going to give us better results. And also because I was not going to use my arm, but someone else's arm that is a little bit more muscular, so probably we could increase that a little bit more. So if this is what I wanted to get out of the V out over V in, I just said, okay, I'm just going to pick a random resistor that is in the middle range so I can accommodate my RI to it. So I just said, well, let's make RF 100 ohms. So with this equation, knowing what I wanted to be the V out versus V in and the RF, I can get the RI, which turned out to be 1,000 ohms. Alright, after I had the 1,000 ohms and my decision of making the RF the 100 ohms, I just took two potentiometers and I made the values to be exact, so that, you know, we wouldn't have many problems of having like 100.1 or whatever. So it's exactly 100 ohms and 1,000 ohms. That's how I picked these values. And then for R31, basically what I did is that we knew from class that R3 is the parallel equivalent of Ri and Rf. So I just ran the calculation and I got that it was supposed to be 90.90 ohms. And for this one, since this one isn't as important as the other two, and as we know it's not even in the equation, I just got whichever resistor was close to this 90.90, and I used the 104.9 ohms for our R31. So this entire part of the circuit basically is going to be de-amplifying. Now let's see how this put together to the other parts is going to make our awesome final general circuit. Alright, so we know how in the general circuit we had first the de-amplification of the signal, which is not going to be used for the arm. We know that part. And then we had the actual instrumentation amplifier that was going to measure right into the arm. And then we had the filtering and amplification, which is this one. However, when I was thinking about the process, I definitely did the filtering first, just because that is the most picky part of the process in which you have to define what your cutoff frequencies are and whatever gain you're going to have from that. And then what I did is, like, when I was doing the trials in my computer to get data, I had a certain amplification in the instrumentation amplifier, and then when I was doing the measurements with the arm, obviously it's going to change because the input is going to change, so I changed that too. So that is why I decided to explain this part first, because this part is going to stay the same throughout the entire process of measuring the data and actually measuring the arm. So this is the third part in the general circuit, and what it does is that it filters the frequencies that we want to pass, and it also amplifies just as a byproduct. This is what we call an active filter, and in this case I'm using an inverting operational amplifier, the LM747. So basically we're going to go step by step saying how I picked the values. First of all, obviously we're going to have just one output signal that is going to come from the instrumentational amplifier. And then over here, we're going to have the first filtering part, which, as we see over here, this is going to be the filtering part related to the high-pass filter. Then over here, we have the filtering part that is going to be related to the low-pass filter. And then obviously we have our common R3 that we need to have always so that our op-amp works the way it's supposed to work. So how I pick the values. Obviously these values over here are just to give power to the operational amplifiers, and just as a note, these are going to be the values, the measure values that I use throughout all my measuring and data to give power to all the operational amplifiers. So those will go obviously down here, connected, giving it power. So the first thing that I did is to decide what my cutoff frequencies had to be. And as we know from the introduction, we definitely wanted to cut as many frequencies as we could below 10, because the range that we want is from 10 to 1,000. That is what the usual frequencies that the arm is going to give us, and the rest we definitely don't want it. So for high pass filter, I wanted to get rid of anything that was below 10 hertz. And then for a low pass filter, I wanted to get rid of anything that was above 1,100 hertz. And why I picked these values, basically because in my other labs, it usually worked to do 100 hertz above the desired frequencies that we wanted to stay. And the one for the high pass filter, this one was a little hard because obviously we know that our blue box is not going to give us very low frequencies, so we can start measuring from down there and to get a good boat plot. This was really hard to choose a very low frequency. Like, let's say if I chose a cutoff frequency of 1, then I didn't have a lot of data to take in first in order to have a nice graph and data. So I did a 9 hertz, which is really close to the starting of the frequencies that we're going to keep, but it's also not very low that we didn't have enough data that we could gather from the blue box. Alright, so we know that the cutoff frequencies are related to the angular cutoff frequencies in this manner. So W of, in this case, is the high pass filter, in this case is the low pass filter. It's just going to be 1 over hurricane RC. So in this case we have the RI2 and RI2, RI2 and CI2 for the high pass filter. And for the low pass filter we obviously have, as we said before this part, which is the RF2 and CF2. So in order for me to choose the values, I knew that I had a very big range with our potentiometers to pick RFs and RIs. The problem was the capacitors. So what I did is that I set forward over here and I said, well, we don't want to have a very big gain, because we know that there's a point in which if your gain is too large, you start cutting frequencies from your input, and that is definitely not what we want. So we wanted to have, you know, like a really good gain that wasn't going to be huge and bad for the operation amplifier. So we know that the gain, I said that I wanted it to be 90 just to pick a number that was in that range. And we know that the gain for this type of design is going to be negative RF over RI, in this case RF2 over RI2. And the negative doesn't really matter, that's just saying that it's going to invert it. So we're going to forget about that negative sign for the rest of this. So what I did is that I said, well, if this is true, then RF2 is equal to 90 times RI2, just reaccommodating this equation, which makes sense. And then from the equations that we wrote before, we know that CF2 is going to be, and this is just from the definition of cutoff frequency, the hard chain of R's and C's. We know that CF2 is equal to 1 over the frequency, in this case the low pass frequency, times 2 pi times 90. In this case I'm just replacing the RF2 for 90 times RI2, because we know they're the same thing. Then what I did is that I solved for RI2 in this equation, and we get 1 over FL times 2 pi times 90 times CF2, which is basically just switching these two together. That is just basic algebra. And then down here, I just brought the equation that we wrote over there for the part that is the high pass of our design, so the part that defines the cutoff frequency for the high pass. And so I said that CI2 is going to be equal to 1 over the high pass cutoff frequency times 2 pi times RI2. And in this case, I just put this RI2 over here from the top, plugged it down here, and as we can see, this is how I plugged it in. The 2 pi's get canceled, and then we get this beautiful equation that is going to help us pick all of these capacitors. So in this case, we have that CI2 is equal to the low pass frequency, cutoff frequency, times 90 times CF2 over the high pass cutoff frequency. And this equation is really nice because it's using two values that we already know because I chose them already, the FH and the FL, and it's giving us a direct equation or the relation between CF2 and CI2. It's really hard to find really good components for the capacitors because we don't have such a big range as we do with potentiometers, so we can like make it to be exactly the value that we want. So after I had this equation, I said, okay, I'm just gonna pick a value for CF2 that is in a good range, that if I plug it into this equation, I'm gonna get out a value for CI2 that is gonna be rational and that I can find in the lab. So I plugged in in the calculator a bunch of numbers, and I came out with this one, 0.9 nanofarads. And this one was good because when I plugged it into this equation, as we can see over here we have the FL, the FH, and then we have 90 times our CF2, which we decide to be this. We get a value that you can actually find in the lab. So this is what I chose to be my CF2 and also what I found in the lab. So this is the actual value. So this is the calculated value from the equation, but thankfully it's also the value of the component that I found in the lab. So that's basically how I chose the capacitors for this filtering part of the circuit. And then it was just plug and chug into the equations over here. Now we can use this part of the board. Basically is reaccommodating this equation, solving for Ri2, and just plugging in the values. So FH times 2 pi times, in this case, CI2, which is the value we found over here. So we get that our Ri2 has to be 1.77 kilo ohms. And I just took a 2K potentiometer and I made it to be the exact same value. So we know over here that is the value that we're going to be using. In this case, we do the exact same thing since we already know what CF2 is going to be from that equation. We can just plug in chalk here, so for our F2, and then we have 1 over FL, which is 1100 hertz times 2 pi times our CF2, which is 0.9 nanofarads, and that gives us an RF2 of 160.763 kilo ohms. And it was really hard to get to this value. Obviously, with the voltmeter, I couldn't measure it so to that exact precision. So what I did is that I just took a potentiometer and made it as close as possible, and I made it to be 160.7 kilo ohms, which is pretty close. So that is the actual value that we used. So now we know what RF2 is, what CF2 is, what CI2 is, and RI2. Now the last part of the circuit was our R32, and in this case it was super easy because we just know that this one is supposed to be the parallel combination or result of RF2 and RI2. So you just do 1 over RF2 plus 1 over RI2, all of that inverse, and then we get, so obviously using the actual values, not the calculated ones, but they're pretty close anyway, and then we get an R32 of 1751 ohms, so 1751 ohms, and I just took a 2000 ohms potentiometer and made it exactly what it was. So that's basically all how I picked all of the different components in this part of the circuit. And just to make sure that my gain was in the range that I was set for in the beginning that I wanted, I took the actual values of Ri2 and RF2 and I plugged it into a nice gain equation for the inverting amplifier, so RF over Ri. And these are the actual values being used in the circuit, and I got a gain of 90.79. We said that we wanted a gain of about 90, so that's pretty good. So this is basically how I chose the filtering, and the amplification, as we said, is kind of a byproduct of choosing those cutoff frequencies and a gain that was in a reasonable range of gain for the op amp. So now let's see how I chose the total gain of the circuit. Alright, to talk a little bit about the part of the circuit that does the measuring and the amplification, we're going to use the circuit diagram. And basically what this is showing is the INA 126 instrumentation amplifier. And here's showing that obviously it has to be connected to power using these values that we set. These are going to be the values that we're going to use in every single operational amplifier that we're going to be using in the circuit to give them the power to work. So obviously it has to be connected to ground, and all of this is in the spec sheet that we were given, how to connect it and which pin goes where. Then this V2 and V1. Basically this is where we're going to connect the electrodes that are going to go into the arm. So we're going to connect the two electrodes that go over here and here directly into this input. And in the case of our measuring of data, which we don't do with the electrons in the arm, what we're going to do is that we're going to connect one of these to the signal that was generated by the amplification part of the circuitry, and the other one we're going to connect it to ground, because we know that basically V1 and V2, what we want is the different potential between these 2 points. And if we connect one to ground and then the signal that we generated to V1, then that is basically just going to give us the V1 that we wanted. So now the only part of the circuit that is a little bit of, you have like a component that you have to choose, is the RG. So in order to know what RG was, I did two different things. First, in order to measure the data, I found an RG that was specifically for that, and then to measure the arm, I did something different. So I'm going to go step by step. First, we should remember that the total output, so the Vout3, if you remember in the general circuitry, the Vout3 is like the total output after the whole circuitry ends. It's going to be the gain from this operational amplifier times the gain of the our active filter that we already said that this gain was 90.79 times the difference between V1 and V2. So with this equation in mind, just remembering that, well, this is our input and these are the amplifications that are going to happen, and this is going to be the output, we can get to the point in which we can figure out what RG has to be. So what I did is that, well, basically this is the same equation copied down, and then I said, well, I want 5 volts. Why 5 volts to be my Vout? Well, because if you plug it into a computer, or let's say the device that is going to know if we want to flex or not the arm, it's going to need some type of switch. And switches usually work with, digital switches usually work with 5 volts or so. So what I said is like, okay, I want a Vout to be 5. I know that my G filter is 90.79, and I'm not going to touch that because that is the byproduct that was given by me choosing the values for the filtering. And I also know that I'm probably going to have something around 1 millivolt for my Vin. So then if we calculate what the GINA has to be, so the gain for this part of the circuit, it says that it's 55.07. And then in the spec sheet it says that the total gain of this instrumentation amplifier is given by 5 plus 8 kilo ohms over RG. So the only thing you can do is calculate RG based on the gain that you want, and I got 159.78 ohms, and I try to make it exact, but in the end I only got 160.0 ohms, which, I mean, to be honest, it's not that bad, but it is close. So this is for the part that we're going to be measuring data to see how the entire circuitry works and see how the filtering is working, and we're going to see the results in a few minutes. For the part of the arm, what I did after we knew all the data is that I said, well, we're going to have a different gain since we're probably going to have a different and more exact input over here. So I used my test subject. actually Nate. And we connected the electrodes to his arm, and then I also connected one channel of the oscilloscope to V1 on the electrode so that I could see how much like the Vn was gonna be. And I saw that the Vn in total was 20 milliamps. And this was just by looking at the oscilloscope. We can see pictures later of what it was, but it was basically channel 1 showing that we have 20 millivolts when he's flexing. I think that we can talk a little bit more about the why it is 20 millivolts and not the maximum 1 millivolt that we talked about. I think it has to do with some noise that was amplified. But anywho, so I got this this value over here, and so that I could know what I wanted my gain in this operational amplifier to be to work perfectly well. So since we already knew again that we want around 5 volts to turn on and off this digital switch, and we already knew that we were not going to touch the gain of the filtering, and now we know our new Vn, we can calculate what the gain of this instrumentation amplifier has to be, and it gave us that it has to be 2.75. And since we remember the equation from the spec sheet that says that the total gain is going to be 5 plus 8 kilo ohms over Rg, we can see that, well, we're not going to get 5 unless we have like a negative number or something here, but there are no negative resistors, so I was just like, well, maybe what we can do is just make Rg infinite, which basically happens when you just open the circuit and let just air be there. And so making Rg be infinite, we're going to have a gain of 5, which is the closest thing we can get to this gain that we want of almost 3. And in the end it worked out perfectly, so we're going to see some of the results. But basically this is how I chose the values for Rg in the case of the arm trial and in the case for collecting data. Alright, so for the last part of our circuit, we have the LED circuitry, and this will have absolutely no impact in the measuring or amplification of the signals that are going to come from the arm. This is just so that we can see the light shining when we flex. Basically, we're going to connect this circuit into the Vout3, which is the final output after we have filtered, amplified, measured, all of that. As we remember from the general picture. This circuit, we worked on it in one of our previous lab, and it's what we called the BGT switch circuit, because it uses a transistor that is going to allow current to flow and therefore make the LED turn on and off depending if the voltage that is coming into the base is the one that we want or not. So in this case, obviously we want the LED to turn on when we have the person flexing. So basically what I did is that in order to measure the values that we have here on the board, I started to looking at the KVLs. So first I look at this big loop of KVL that we can see right here. So we know that obviously everything's equal to 0. Let's say we start from right here, so we're going to go through the VCC LED, and then we're going to subtract the VLED, right here, and then we're going to subtract the ICRL, which is obviously the voltage across this resistor, and then we're going to subtract the VCE, which is the voltage difference between the collector and the emitter part of the transistor. And just as a side note, I don't know if I mentioned before, we're going to be using the 213904 transistor for this circuit. So if we solve over here for our RL, basically we have all the values. We have 15 volts, which is our VCC, which we said before that is how we're going to power most of the devices in the circuit. If you look at the spec sheet guidelines, you're going to see that any red LED is going to have a voltage difference of around 1.8 volts. And then obviously from our transistor guidelines, we remember that our VCE, so the voltage difference between the collector and the emitter is going to be about 0.1 volts. And since we've been working with LEDs previously a lot, we know that we want the current flowing through the LED to be around 20 milliamps, so that it's bright enough we can see it. That is like the optimal current that has to flow through it. So now that we have all these values, we can calculate what RL is, and we get a value of 655 ohms, which is the actual value that we got and put into the circuit by using potentiometers. Then if we look at this smaller loop over here, so that we can figure out the value of RB, basically we're going to do another KVL, and we're going to have V out, and then we're going to subtract RB times IB, and then we're going to subtract the voltage difference between the base and the emitter, that is going to end in ground. And so that's basically going to be this equation over here, and if you solve for RB, we get V out 3 minus VBE over IB. And just because I measured what was V out 3 when we were doing the flexing so that I could get the exact value for the LED that I wanted, I saw that we were having a V out 3 of 3 volts instead of 5 volts, what we were expecting. And we're going to talk a little bit more about this in the discussion part. But definitely I just wanted to make the circuit of the LED work, so I inputted the V out 3 to be 3 volts. And then the VBE, we know it's 0.7 volts from transistor guidelines, or yeah, that we know from before. And then the IB, we know that this IB has to be correlated to IC. And so we remember that this has to be at least 100 times more than IC, which is going through the bigger KVL. So as we said, we have all these values, so now it's just plug and chug and know what RB is, and we get 11,500 ohms, and that is the exact value that we put into the circuit using potentiometers. So this is basically how I figure out the values. The circuit diagram, I got it from that old lab that we used before, the BGT switch, because it's basically what we wanted. We wanted a switch, and we wanted the LED to act as that switch, to turn on when we were flexing and turn off when we were not. So this is basically all the parts and the design elements of my circuit. Now we're going to move on into explaining a little bit the results and what we think about them. Alright, so I'm going to talk a little bit about how I got the results and the data measuring. Obviously, by the end of the results section, we're going to see a video of how everything worked out with the arm and what we can see in the oscilloscope, which is like the final test. However, in order to do that, I needed to gather some data first. So the data gathering goes like this. First, I put one of the channels of the oscilloscope into where, well, exactly at the place where the de-amplifying signal was being emitted. So that's going to be our V in, because that is what we're pretending to be the arm, right? Then the V out is going to go at the very end of the circuit, what we call, or what I call in the general circuit, V out 3. So after that, using the oscilloscope, I was able to measure the frequency, and obviously I was changing the frequency in order to make good measurements. Also, in the oscilloscope, you can read what VBP in is and VBP out just by looking at channel 1 and channel 2 measurements. And also, if you move the cursors, you're able to get delta T. So these are basically the 4 things that I needed to gather as raw data, and with this I was able to get the entire information that I needed. So with the frequency, obviously you can get the log of the frequency in order to make some of those graphs that we really need. Also, with those graphs and having the log of the frequency, we are later able to find what the cutoff frequency is for the experiment so that we can compare it to the ideal. Having the VBP in and VBP out, well, this gives us our H of omega by just doing VBP out over VBP in. And just as a side note, VBP means like the voltage peak to peak. So given this, I can see what my actual total gain maximum was, because we're going to see what is our maximum transfer function, and that is going to be the maximum number of the output compared to the input. So using this data, we also can compare what we wanted to be the total maximum gain of the circuit, the ideal one. Then, since we have our transfer function, now we can do g of omega, which is basically doing 20 times log base of 10 of the transfer function. And by doing this, we can compare the ideal graph to the experimental graph of what it should look like. And also, we can see the roll-offs of each one of these and compare them to the ideal. Then by measuring delta t, we're able to get the phase shift that we're going to get in each one of the frequencies that we're measuring at by just doing the frequency times 2 pi, which gives us W, times the change in t. So now that we know exactly how we're going to use this data, I'm going to talk a little bit about how I get the ideal values, because I'm just going to show pictures, and it's better if we understand how I decided to, why I decided to use this as the ideal values. So when I'm comparing my g of omega, the ideal versus the experimental, is basically running a MATLAB script that says, well, we're going to take the transfer function, and just like the same as before, we're going to use the equation for the transfer function for the bandpass filter, which is the part of the low-pass filter times the high-pass filter. And in this case, this is not an approximation. This is the exact thing. And then we remember from class that the transfer function is also going to be multiplied by the gain that we're getting in the filter. But since we are looking at the entire circuitry, then we're going to make this not just negative IRF over I, but the entire gain of the circuit. So this just gives us the final H of omega. So in MATLAB, basically what I did is that I reused the script that was for the bandpass filter, which had this already written for the ideal case, and I just added this element over here, which is the plus 20 log base of 10 of the total gain, because we know that if we take this H of omega here and we multiply all of this times 20, and well, actually first we take the log base of 10 of all of this, and then we multiply times 20, we can separate multiplications at a log into a addition. So that is why we're going to have 20 log base 10 of whatever bandpass filter we've been using all this time, the same equation, and we now just need to add 20 log base 10 of the total gain. In this case, I'm going to be using the theoretical gain, just because we want the theoretical g of omega in order to compare it to the g of omega that was measured using the transfer function measurements. So that is how we're going to compare this. Then for the roll-off of the slopes, we know that that hasn't changed. The slope is not going to change because of the gain. We're still expecting to have 20 decibels per decade for each one of the, well, for the positive roll-off, it's 20 decibels per decade, and for the negative roll-off, negative 20 decibels per decade. So we're going to compare this by this being the ideal, and we're going to compare it to what we got using an Excel spreadsheet and only taking the best fit line, a straight line of the part that is the roll-off of our measured g of omega. Then in order for us to know what our cutoff frequency was, the ideal versus the experimental, we're going to take the 3 dB point. Basically in MATLAB, I'm going to write, tell me what is the maximum of g of omega, the measured g of omega, minus 3 decibels, which is what we do to get the negative 3 dB point. And then I'm going to go and make a line in the graph so that I can find the intersecting points of that line and our graph. And that is going to tell us what the ideal cutoff frequencies are, and also by intersecting the red points, which we're going to see later on. Those are the real points in the graph in which we're going to be comparing ideal versus experimental. That is going to give us the real cutoff frequency. Alright, and final but not least, we're going to have to talk a little bit about the angle. And basically I used, as we know from before, since we're not taking into account the deamplification, the operation amplifier that does the deamplification, then I just have two operation amplifiers, which is the instrumentational one and also the INA 126. So in the end, we just have one of those operational amplifiers that is going to be inverting the signal. So we're going to have, for phase shift, it should look exactly like the bandpass filter, but with a negative sign in front of all of it. So usually before, for the bandpass filter, we had negative tangent, inverse tangent of omega over the low pass omega, plus, no, we had negative, so minus tangent inverse of omega over the high pass omega, plus p over pi over 2. So in this case we have positive, positive, minus because we inverse the signs. And so this is what it should look like, and we're going to compare it to what we got over here using our change in t. And just as a side note, the way that I calculated the total gain over here, and we talked a little bit about this when I was doing the design, is that I just did the total gain as the gain of the INA times the gain of the filter. The gain of the INA, as we talked about it, is 5 plus 8 kilo ohms over Rg, and our exact value for Rg in the circuit was 160 ohms. So if you plug this in here and then multiply it by the actual 90.79 gain that we got from the active filter operation amplifier, we get a total gain of 4,993.45. So this is going to be our theoretical total gain, which we use over here, and which we're going to compare later on to the maximum gain that we can see we get for the transfer function, so that we can get percent differences.
It might seem crazy what I'm about to say. Sunshine, she's here, you can take a break. I'm a hot air balloon that could go to space with the air, like I don't care, baby, by the way. Because I'm happy. Clap along if you feel like a room without a roof. Because I'm happy. Clap along if you feel like happiness is the truth. Because I'm happy. Clap along if you know what happiness is to you. Because I'm happy. Clap along if you feel like that's what you want to do. Here come bad news, talking this and that. Well, give me all you got and don't hold it back. Well, I should probably warn you, I'll be just fine. No offense to you, don't waste your time. Here's why. Because I'm happy. Clap along if you feel like a room without a roof. Because I'm happy. Clap along if you.
Hello, so we're about to try Maria's circuit to see Nate's muscles. So right now, he's all plugged in. Say hi.
Hi.
Alright, so we have the two electrodes right here, and then we have ground in a bony area right here. They're both connected to your circuit. We can see that this is the ground one, which is connected to ground through the battery, which ground is this one. And then we have the two electrodes coming right here into the instrumentation amp. Then the signal is going to go through all of these, which this make up the filter. And then this is just the little LED circuitry. And here we're going to see the signal in yellow is going to be the one coming in, and the signal in blue is the one coming out. So Let's see what happens when he flexes. 1, 2, 3. Rah! Do you see that? 1, 2. Well, okay, well, there he goes. Stop! Show off. But we can totally see how it's working. Alright, we're gonna try to make it pull. So, like, 1, 2, 3. 1, 2, 3. Awesome! Now let's look at the LED. 1, 2, 3. 1, 2, 3. Great! Let's look at this one last time. 1, 2, 3. 1, 2, 3. I said 1, 2, 3. Okay, there he goes. Alright, awesome! Alright, so to measure how much the input is going to change, we're going to see when Nate is not flexing at all, which is right now. And as we can see, we have 12 millivolts coming in. Obviously, because of amplification, that's probably some noise. So now let's see what happens when he flexes. 1, 2, go! We need to wait for the oscilloscope to switch. Hopefully soon, because he might die out of a... Come on! Oscilloscope. Oh, 20 milliamps. Look at that. Awesome. We can see how the little light is going on. Alright, conclusion. Finally, it worked. Yes, it was really cool to see how in the oscilloscope, when the person was contracting, or in a case, muscular Nate was contracting, you could definitely see the oscilloscope going crazy, and then when he wasn't, it was a flat line. So that was really awesome. Now to talk a little bit about the actual numbers that we got. For the total gain of the circuitry, we got a percent difference of 1.91. That is really good. I think that this is saying that all the rules that we've been applying and all the calculations and probably the use of potentiometers actually really helped us to get the exact gain that we wanted, and that is awesome. Now a little bit about our G of omega. We saw that it was almost perfectly in the place where our theoretical G of omega was supposed to be. All the measurements for all frequencies were below 3% difference from what we wanted. Then from our calculator, experimental and theoretical cutoff frequencies, we have that the cutoff frequency for the high pass filter, part of the band pass filter, was only 2.39%. That is really good again. All of this is within our sanity check. So that's pretty good. But then for the cutoff frequency for the low pass filter, we have 15.0%. So in this part, I don't really know what made this huge difference between both of these, but just by looking at the graphs, I can see that probably I needed to take a little bit more data around the low pass cutoff frequency, just so that probably that would have given me a better number over here. Because definitely is not as close on this side of the G of omega as it was to the other side, and this is, you can see this from the graph. So I think in this case it's just merely just probably I just needed more data on that side. Now to talk a little bit about the roll-offs. Well, the roll-offs are usually complicated, and I remember from our first filter graph, the roll-offs were the one that I had the greatest percent difference, and for this one it wasn't really that bad for the roll-off with high frequencies. And in this case, I think that the difference between these two and the fact that we have a greater percent difference of 20.5% for the low frequencies roll-off, I think this is because we obviously had a stopping point of the frequencies that we could go low. So our blue boxes are not going to go very low frequencies. I think their lowest frequency that we could have from them is around like 5 or 3, or I think the minimum will be around 2 hertz. But so this means that we didn't have much space to take data points that were not already affected by the cutoff frequency. So this is probably why this percent difference is so inflated. if we had had a better probably signal generator with smaller frequencies that we could say, alright, let's put like a 0.2 or something like that, probably a relief would have been a little bit better. Alright, so what to do next time so we make it better? Definitely, I think that just because it was before Thanksgiving, I kind of rushed through the process a little bit, even though as we can see we got really good results and the circuit definitely worked. We'll probably spend a little bit more time maybe looking at the data for so that we can calculate all of these before taking down the circuit. It would have helped. Also, I think that it's important to notice that it was really surprising that for people who have a lot of muscles, they generated, or the person who I tried generated about 10 millivolts, which is a lot more to what we were expecting. Also, I thought it was interesting that it was better when I measured the incoming signal right into the oscilloscope, and then knowing what gain I wanted to put into my INA 126, then trying to figure out first the gain and then trying to measure this. Because if you look at how much the person who is contracting his muscle, if you look at what the V in is in the oscilloscope, you can figure out the exact amplification that you want in your circuit. And just finally, I think I can see that pretty much all the measurements and all the data was really close to what I really wanted to happen or what was drawn on paper. So I'm really proud of myself, and I hope you like this video.